Welcome back to System Software. Today we are continuing in compiler foundations. Today we're going to talk about parsing, some of the kind of philosophical issues behind it, some of the technical introduction to it, and with lots of examples of how we build and write interpreters and compilers using this language, the theory of languages. Okay. So remember last time we talked about, this was before the exam, but we talked about how a source file becomes a running program on your machine. And this was the picture that I showed. You have your source file. It goes through the preprocessor for includes and macros. Then it goes through the compiler. What does the compiler produce?
GCC.
Assembly. The compiler produces assembly code. GCC is the tool for doing compiling. Assembly code gets assembled into a binary object file, which has the binary machine code of the instruction set of your machine that you're compiling for. Linker, what does the linker do? Makes it executable. And how does it do that? Yeah, brings together multiple object files and any libraries you have, as well as the C runtime, which sets up main and calls main for you. And then how does this executable get turned into a running program? Well, here on the screen.
exec.ve.
Yeah, the exec function. What does exec do? Does it create a new process? Changes the running program. That's all it does. It just replaces a current processes, memory locations that store the program, and replaces it, and then updates the program counter to start running it from the beginning. Yeah.
So the loader actually will do the //
Effectively, well, actually, if you're looking at my shell, my sh program, you're writing what bash does. When you do / and run it, or you run any command that's a program, the bash shell will call fork to make a new process, and will call exec. So yeah, this is exactly what happens when you do // or really just put any program name that's in the path, but that you give a full path to on the command line. So mysh is showing you how to use the kernel, use the kernel's loader to actually make a running program. What's that?
This is all called the kernel, right?
This is not all the kernel. So this part is the kernel, and these are the system tools. This is part of the tool chain. So this is like the system software here, and this is the kernel. So the kernel and the system tools are designed to work together to have the right formats, to set up everything in the right expected way, to make sure that they're all working on the same instruction set, the same machine. But yeah, so if you want to see after the system tools how stuff works at the kernel level, take an operating system course. So that'll go into how the kernel itself is designed to give you exec and other system calls. All right, so let's zoom into the compiler part. So we're going to be working here. We're not going to be compiling C. We're going to be compiling this custom simplified language that I'll explain next time. But we're going to be working in the compiler here. So in the kind of, I forgot to bring my notes. In the really simple version of the compiler, there are two pieces of a compiler. The front end processes the input language, and it produces a syntax tree. And I'll describe what that is in a second, but it analyzes the syntax, the grammar of your input file, and stores that as a structure in memory. Then the back end takes that structured view of your input program and uses it to generate machine code. Yeah?
It's kind of like the pipe, because it has in essence like a read end and write end.
I mean, you can think of all modularization this way. In any system, even like a car engine, you have modules like the transmission, the engine, they each have a well-defined function that they do, and there's interfaces between them. You can think of more of pipe as an instance of modularization rather than the other way around. So you'll see this probably when you get to processes. If you haven't taken processes of object orientation, that's probably, if you haven't seen it before, where you'll first see this notion of building software architecture, where you're building pieces of software or systems as components that work together. So you could write a compiler that's like literally separate programs and use pipe to construct the system as these multiple components. But in practice, people just write these in one language and then use the language tools like objects in order to create these modules. Okay, so let me make a very simple diagram of what this looks like. It's moving ahead. All right, so we have our source file. So in our previous diagram, it just went into the compiler. And what was produced by the compiler? Assembly, right, machine code, or machine code in an assembly format. So inside the compiler, we can break this down into two rough phases. The front end
Inputs.
and the back end. Yeah, so what's the input to the front end? It's the source code. And what it produces is a tree representation of the input program. It's a syntax tree. Just like in human language, you probably learned about syntax in grammar school. It's called grammar. Well, now it's called elementary school, but grammar school, because I guess you would historically be taught grammar, like probably Latin grammar or something. So the front end produces this syntax tree representation of the input, and then that syntax tree can then be used to generate machine code. So that's the kind of like big picture view of compilers. And now in this class, we're going to have a very simple language that we're going to process, and I'm going to basically give you the front end. Antler is the front end. So you won't have to write the front end, but you'll have to learn how to use it. And then the kind of, to give away the end here, generating code from this is basically just tree walking. So in CS1 or CS2, if you learned about trees, who did tree traversals? I think everyone probably did tree traversals. So if you learned about tree traversals, you'll see a real-world application of this for a system tool, not just some academic exercise, but how we can actually process languages using just basically tree walking algorithms. Okay, so questions about the overall structure, the really core structure of a compiler. Yeah?
How does the backend produce like the file dot something?
We'll go over that. I'll show an example of how this will actually work using arithmetic expressions. We'll go over an example of this. All right, so that's the kind of, any other questions about the kind of course? Yeah?
It's probably a very stupid question, but would this be the same process for any sort of code language as well?
Generally, yeah. So the kind of standard interpreter compiler is designed this way, yeah.
It's only for Unix?
Say again?
Would it only be for the Unix system? Or?
No, this is all compilers work this way. This is kind of the standard.
Java?
Even Java. Yeah, any language you can think of today, programming language, works with this way. They have a front end that turns the source code into a syntax tree and a back end that turns that syntax tree into machine code. And interpreters work very similarly, where they have a front end to process the language, and instead of generating code, it evaluates the value of the program. So yeah, I would say all compilers today. Now, there are LLM, large language model, AI-based approaches to translation, which don't use this architecture. But the current programming language world, any language that I could think of, that you could probably name, uses this architecture. Yeah?
Can you explain what you mean by syntax tree?
Yes, we will get into that. We'll get into that more than you probably want. Yeah.
Is a syntax tree where like a lot of resources can be held up? And so, like for example, with Python, how it's not very efficient is because a lot. Is that because of how complicated the syntax?
Actually, no. The front end has very little impact on the performance of the resulting program,
Oh, okay.
and that's actually the back end. Really, yeah, the back end is really what drives performance, I'd say. So the Python back end is not generating file.s, it's running the program. It's evaluating the value of the program. So yeah, somebody asked before why interpreters tend to be slower. I don't have the exact precise answer. My suspicion is because it's a software emulation that's instead of the hardware machine. The hardware machine will run operations much faster than a software program that's running on top of that machine to evaluate it, I think in general. I don't know if that's scientifically true. You can go on Stack Overflow and see all sorts of arguments about performance in languages, but I think generally software emulation is slower generally than hardware emulation for like a similar architecture. But, take it with a grain of salt. Prove me wrong if you can find some evidence. Okay, so that's the basic structure of a compiler. Usually it's divided into let's process and it kind of makes sense because what does a compiler do? It takes an input language and generates an equivalent program in a different language. So the front end part is processing that input language. The back end part is generating your output language. Okay. So perhaps confusingly, many real-world compilers have a so-called middle end, which is a very silly term because I don't know how the middle can be the end. But because traditionally you had back end and front end in the compiler, so there's this middle end that many real-world compilers use. And what they do is here, instead of going from front end to back end, their front end will generate an intermediate representation. This is so this depends on the language or compiler or interpreter that you're looking at, but this will be some simpler version of a programming language. It'll be something kind of in between machine code. Machines have finite registers and very, very specific instruction sets. Programming languages have high-level constructs and types and things like this. So intermediate representations, common ones, are typically somewhere in between. So for instance, LLVM, which is a very popular intermediate language for compilers, is like a machine where it has registers, but it has infinite registers, unlike a machine. And so this intermediate representation is used in a middle end to then do some, so this part here is the middle end. So let me put the diagram here. Is this intermediate representation. And then the intermediate representation is what's passed to the back end to make your assembly file. So why bother doing this? Why bother making a whole other language and having a separate front end and back end for that other language in order to generate code from it? Yeah.
I imagine it would help with various hardware, like distributing stuff across various hardware. If you just have one language that you can write to, basically running on top of the VM.
Yeah, so there's a couple answers there that are both good answers. So one is if you want to target multiple different architectures. So somebody asked before, do you need a compiler for every language? And my answer was you need a compiler for every front end or for every input and output language. So if you want a C compiler for x86, you want a C compiler for ARM, you need two compilers. But one way that you can mitigate this explosion of the need of compilers is to, instead of compiling to x86, you compile to an intermediate representation. And you're still going to need a backend to generate IR, intermediate representation. I'm going to use the abbreviation IR, to generate x86 from that. But now when you go to, if you want to port it to, say, ARM, you no longer, this front end can be reused. You can have C to the IR, and then you just make a different back end that generates ARM code. And so it doesn't completely remove the need to port the compiler, but it makes it easier to do. Another way to look at it is, because this language is not machine code, it does not have the idiosyncrasies of different machines, writing this compiler is actually easier. It's generally easier to write a compiler, a front end that goes to intermediate code rather than writing it to go to x86. And your colleague also pointed out virtual machines. So certainly, yeah, this IR doesn't necessarily have to be compiled or used to generate machine code. You could just interpret this IR directly. And so when I said, I don't know, a couple of lectures ago that most programming language implementation use a mix of compilers and interpreters, the Python interpreter doesn't actually interpret Python code. It generates a virtual machine code. It actually is like a compiler to an intermediate representation. And then that intermediate representation gets interpreted. So Java is also something similar where you have a compiler to Java bytecode, and that bytecode gets interpreted by the Java virtual machine. Okay, so yeah, that's all the reasons to use, that's some good reasons to use intermediate representation. Let's see if I covered everything. Oh yeah, so there's also another important one that, so one big part of what compilers do is optimization. Instead of just generating, so last time we talked about the assembly language representation of a for loop and whether you actually needed to do jump for a for loop. And not in all cases, right? You can imagine for loops that have, say, a constant number of iterations that you wouldn't need a jump for. You could just literally copy the body however many times you need to in order to execute that loop. So what modern compilers do is they try to find more efficient assembly code, either in memory or runtime, to make more efficient output programs, because there are many, many ways to generate equivalent versions of your input program. And so having a middle end allows you to do optimizations that are independent of any particular machine. So there are lots of common optimizations that work on basically all architectures, and you can make this independent of C, and you can make it independent of any particular architecture. So here's a diagram of what that looks like from the LLM world. So LLVM is a super popular compiler infrastructure that's used for many industrial strength compilers. And so here's a picture of its front ends, back ends, and its middle end. So LLVM is originally the name of, the LLVM IR, intermediate representation, was the name of the intermediate representation that this guy, Chris Latner, designed. Actually, when he was a master's student, he designed this. So he designed this intermediate representation for compilers, and that's separate and independent of any particular input language or any particular output language. It's its own language. And over time, this community has built up several optimizations and analyses that can be done on this IR language, so that when you want to go create a new compiler, like let's say you want to build your own language, you can just make a new front end. You can design the language and then generate LLVM IR, and now you'll have really a pretty industrial strength compiler for your language. Or if you want to port C to your new architecture, say you have a new machine that you built, then you can use this and reuse this entire front end and middle end infrastructure and just change the back end in order to generate different machine instructions. Or if you want to explore different optimizations, you can use this architecture. All right, so one sort of a little quiz here. So how many front end languages are depicted here? 5, right? How many back end architectures are depicted here? 5. So how many compilers do we have here? 1. Okay. How many unique pairs of input and output languages do we have? 25, right? 5 times 5. So if we were to write a compiler for each one of these combinations, we need 25 compilers. But with this architecture, we only need 5 front ends and 5 back ends. So, and then we have to write this middle end. So we have much less work in order to build new compilers.
I wonder where Java is in this. I wonder where Java is in this. Where's Java?
So I think there was a project to try to convert Java to IR, but Java is kind of designed around its own bytecode language and its own virtual machine. So you could, in principle, compile Java to machine code. But yeah, people typically it has its own compiler architecture for compiling to Java bytecode. All right, questions on this? Yeah.
Is there any reason why it's better than just like a normal compiler?
So it's not necessarily better. What it's better for is if you have many input languages that if you want to build lots of different compilers, support lots of different input languages and lots of different back-end architectures. This is less work because you can reuse existing work from other compilers. So better or worse, it's sort of hard to say that absolutely. If you have an engineering goal and one of your goals is to support many different front ends and many different back ends, this is a good architecture for that because you just write less code. You have less duplication. If you want a super customized interpreter or compiler, like Java, for instance, has its own specific back end, its own specific virtual machine, then, and this was also developed after Java was developed, so there was no reason for them to port their work to LLVM. This IR is also, while it is technically independent of any front end, it's very much designed originally around C-style languages and compiling to machine code. So it's not necessarily the best for, say, Python interpretation. All right, so here's a textbook diagram of the phases of a compiler. If you're interested in actually the full compiler flow and how to actually build this, take my graduate compilers class. I'll just throw this up here, and we don't have to talk about this. You won't have to do much about this. So take my graduate compilers class if you want to actually dig into the details of a full compiler. Okay, so let's get a little philosophical here. What does this mean? Okay, so it means
Order of operation.
it means order of operations. So I hear 2 times 3 plus 1. I hear order of operations. So so that's what it means. And what's the result? What's the end value of that? 7. Okay. Some people say. Anyone say anything different? Number. Anyone ever program in like Fortran, like the 1950s Fortran before? Probably not, right? So that Fortran did not have the order of operations we learned in school. It would actually compute this as 1 plus 2, 3 times 3, 9. Just to sort of illustrate to you that we've got some built-in interpreters in our head. All right, let's do another one. This one, like you'll see this on the internet sometimes. What does this mean? Or what's its value? Okay, what's its value? And what does it mean? What's that? 9? Say again? So we get one answer that says do the parentheses first. That's 3, and then multiply by 2, right? 6, and then it's 1. We had another answer that was what? What was the other answer?
9.
Because 6 divided by 2 is 3. Who's right? Who thinks they're right? So just to kind of illustrate for you that in order to interpret the meaning of this, you have some rules in your head. They may be implicit, but you have some rules, right?
Right.
Now, to really highlight this, what does this mean?
Japanese, Korean, Vietnam.
Who here actually knows, who here recognizes this? So we have one probably Chinese speaker, native Chinese speaker,
Japanese,
right?
Vietnamese.
Or Japanese speaker. So someone want to take a guess what this means? Yeah.
I know the first character is ichi, which means 1, the second character with 2 lines is ni, which is 2, and the third one is san, which is 3. I don't know.
Okay, so somebody is saying the meaning of this is 1, 2, and 3. All right, so the person actually knows this. What does this mean?
I honestly forgot originally. I got Japanese.
Oh, you're Japanese. Okay. All right. Well, there's no Chinese speakers.
But my friend is Chinese, but I can speak if I can read it.
Can't read. Okay. So no Chinese reader. Somebody's using an app to do this. What's it mean?
1 plus power 3,
1 plus 2 times 3. This is 1 plus 2 times 3 in Chinese. And what I want to illustrate to you is that everyone had really strong opinions about what this means, but everyone's like, what does this mean? So just to point out to you that these symbols to a particular interpreter has a meaning, and it actually has the same meaning as this, coincidentally. And to you all who learned, the Arabic numbers, I mean, Chinese students also everyone learns the Arabic numerals. I think worldwide, right, who's learning math. This has a particular meaning. But the point is that these symbols themselves, so there's no intrinsic meaning to these symbols, because this means to someone the same as 1 plus 2 times 3, but to most, actually all of you, you had no idea what this meant. Because the symbols themselves don't have any intrinsic meaning. Now, you have mnemonics like, well, this is a single dash, these are 2 dashes, these are 3 dashes. And so you can use that as kind of a mnemonic to help you remember. It's a very kind of physical symbol. But the symbol itself has no intrinsic meaning. I argue. Now, you can take it with a grain of salt, argue with me, tell me if you think differently. But they don't have intrinsic meaning, according to me, so says me. So what gives symbols meaning? So go ahead. Yeah.
Somebody asked the question of this.
Say again?
Somebody asked the question.
Yeah, please.
Basically, it's just like you have these rules put in place by human beings that say that kind of gives meaning. You can kind of learn it, in school or from your parents, whatever. And I guess just like if we're going to do this in coding, it's the developer that gives meaning. If that makes sense.
Yeah, so what your student said, which is I think exactly right. One way that you ascribe meaning is you define rules that interpret the meaning of the language. And this is exactly what we're going to build a machine to do. So for humans, language is very much, if not built in, it's probably built in. It's at least kind of implicit. You don't really think about, when you saw this, you didn't really think, all right, well, this is a straight line and it maps to the value 1. You didn't really think of that. You just kind of automatically in your head started computing it. But that's why I showed you this, to say like, well, that kind of stumps you, right? But if you had a set of rules, and this is very close to Turing's thought experiment, the Chinese room thought experiment, that if you had all the rules and you could apply those rules, you could actually fool someone into thinking that you spoke Chinese or you understood what this meant. And so we're going to do something very similar when we build our compiler. We're going to, the machine itself is not going to understand any of these symbols, but we're going to write a set of rules that's going to interpret the meaning of this. Now we're going to interpret the meaning by translating to assembly, but you could also interpret the meaning by producing the resulting value. That would be an interpreter. So there's a couple of kind of some philosophical background to this. If you ever heard the expression, the moon versus the finger pointing at the moon. So symbols are not the thing they represent, they're pointers to them. If you've ever been confused by pointers in C, you probably have the same problem, because if you try to like subtract the pointer, well, you're subtracting the address, not the value. And so you can think of symbols as like pointers to something. It's pointing to something else. There's also a kind of famous expression, the map is not the territory. You know, if you rip a map, you're not going to cause an earthquake, right? The map is just a representation of the world. And in kind of science, philosophy of science in general, we make like mappings to the world that have some preservation of behavior. So, you know, when you have an equation that computes, say, the path of a ball through space, you have some preservation of some behavior of that movement of the ball, but it's not actually the ball. It's just a math equation that describes the movement. Okay, questions on that? Thoughts on that? Disagreements? This is sort of a philosophical assumption. There's little to kind of prove here. But it is the philosophy that sort of is the basis of building compilers. Okay, and so in our world, for programming languages, we saw this same thing when we looked at building a really simple compiler last time. Remember, we read in an ASCII character, but just to kind of refresh your memory, these ASCII characters, even the ASCII character for the number 1, had the decimal value in the machine, in the machine's representation of numbers. When it represents that ASCII character 1, it uses the decimal value 49, or the binary data that's equivalent to the decimal value 49. And so this also illustrates how the symbols themselves don't have the meaning that you expect. It's just a symbol. And in our compiler, what do we have to do in order to interpret interpret that ASCII number? Do you remember what we had to do? Remember, so I just subtracted the ASCII over 0. We just converted it. We converted the ASCII symbol 1 into the machine value 1. We had to convert that. That's kind of a very basic interpreter of a symbol. I guess a kind of fun bonus exercise would be to write a compiler that takes Chinese. You could do that. Or a little calculator that takes Chinese characters. You can use Unicode to do that. Okay, questions on this? Questions on, yeah?
I would be curious to see, like, have you heard about, probably heard, like, new language, FOO?
No.
Someone made a language where it's, like, literally could, like, do all the stuff we do in C, but you literally call it, like, combinations of FOO.
Oh, yeah. Yeah, there's a bunch of these, like, so-called esoteric languages, like Brain F is a popular one. Yeah, so this goes back to the core of what computation is. So to reference Turing again, he came up with this Turing machine to try to describe what computation was, and it turns out that there was other attempts to define computation, like the Church's lambda calculus. They've been proven equivalent, and I think the programming languages that we use also are equivalent to these machines. So yeah, you can use lots of different representations to express the same computation. Okay, questions on symbols versus meaning. So it's kind of a deep philosophical issue, but the main thing I want to point out, at least from the machine point of view, is that these symbols have no intrinsic value to the machine. They are ASCII codes that a program will draw a glyph on the screen for you, and that you as the compiler writer will have to interpret in the way that you want it to, in the way that you define. So you could define a language where this ASCII symbol means division, if you wanted. That might be confusing, because everyone sort of expects this to mean addition, but you could define that. You could define this symbol here to mean 70, if you want, or to mean a string. You could define it however you like. Yeah?
Somehow, if, because I know that you said that someone is kind of like plans for this and maybe meanings defined by the programmer, but what if different programmers have different meanings and someone points to both of them? How would
Yeah, so if you have one symbol that means multiple things, that's actually a really good segue into syntax. But programming languages do have different meaning, right? So in some languages, the plus symbol means concatenation, depending on the type, right? So like in Python, for instance. Has anyone ever programmed in a language where plus is concatenation? Okay, not many. So yeah, C has very little of this overloading of operators, where the only overloading it has is that plus, and plus mean you can use it for floats and you can use it for integers, right? At the machine level, are these the same assembly operations, a floating point addition and an integer addition? No, right? They're different operations, but in C, that same symbol is being used for both. So you do have this case actually quite a bit in languages. And so each language defines its own meaning of its symbols. There's like a shared lineage of a lot of these languages, but like your colleague pointed out, there are these esoteric languages like Mu and Brain F that use a very restricted set of symbols to be able to express computations that you can do in other languages as well. Do you mean the ambiguity that you read about? Yeah. So as Terence Parr pointed out in the book, ambiguity is kind of annoying for development, for programming languages. You might imagine a language that would allow ambiguity, but in the programming languages that I know of, ambiguity is removed. So the languages are unambiguous. Or at best, the language designers will say, this is undefined behavior. And, the compiler can do whatever it wants, or just never do that. I don't know if that's really ambiguity, but it's up to the language designer to say what the language will do. And with deterministic computation, it's usually easier for a programmer to know that there's only a single meaning of that set of symbols. Now, in that, if you did the reading, they also pointed out there is ambiguity in language, like you can never put too much water in a nuclear reactor, which is kind of a scary and silly one, which has two meanings, right? It can mean put as much water as you want, or you don't put too much water in the reactor. And we'll talk about ambiguity, syntactic ambiguity as well, just in a bit. But yeah, I think from a programming language design point of view, it'd probably be confusing for your developer if different compilers did different things with the same construct. And that does happen with C mostly because of undefined behavior. No problem. All right, so let's talk about syntax trees. All right, so who did sentence diagramming in school? This is never done before. I feel like there's fewer and fewer people. Who knows what sentence diagramming is? Well, okay, so not many. All right, so let's diagram this sentence. What's that? Yeah, basically. Yeah. What's the subject of the sentence? The boy. Who says the boy is the subject of the sentence? Who thinks it's something different? Okay, so even those who never did sentence diagramming, you still sort of know about this sentence structure, right? You know that there's, in English at least, the subject is usually first, at least in some type of sentence. Say again?
Isn't the just a preposition? So
The is an article. It's not a proposition. Proposition to isn't a preposition. But we can call this a subject phrase. So I'm not an expert in English or language grammar, but I'm going to call this whole phrase the subject. Yeah, and that's actually a really good point, is that you could actually break down the subject phrase into smaller pieces, which we'll see. All right, what about the verb? Where's the action? Yeah, where's the verb? Went, right? So here's our verb or verb phrase. It's a degenerate phrase, it only has one. What about the object of the sentence? Yeah. Store. So I'm going to call to the store the object phrase. What kind of object is this? Direct or indirect? It's really a shame that nobody learns grammar anymore. Who says indirect object? Who says direct object? It's indirect, because there's a preposition saying to the store. The boy went. Am I wrong? Am I wrong? Is that right? Who says indirect? Nobody? Okay. I'm pretty sure it's the indirect object. So, I think. So if you said the boy went to the store, that would be a direct object, I think.
Yeah, I don't know.
Okay, well, let's say, how about a different one? The boy ate at the store. Is the store indirect or direct? Indirect. What if the boy ate lunch at the store?
Direct.
Lunch is direct, at the store is indirect. So I think it's indirect. Anyway, there's not going to be questions on this. Don't worry about it. But I want to point out to you that you can create this hierarchical tree of the sentence's syntax. So a syntax diagram is really just a sentence diagramming is really just syntax trees. It's breaking the words down into groups that are associated with the parts of a sentence. Yeah.
Can there be more than one subject phrase?
In a sentence?
Yes.
So in the like current understanding of English grammar, if you said like the boy and the girl went to the store, you mean like that? There's two subjects.
Yeah.
So how would we solve that? How would we solve two subjects? What's one way to solve it? Yeah.
Can I just call them, divide them into like two subjects? We have two of them.
Yeah, we could take our subject phrase and we could break it up into, say, let's say it's a and phrase. And we could have two pieces of this and phrase. The boy, the word and the girl. So we still have a single subject in our sentence, but we can further break down the subject part of the sentence into multiple pieces with new descriptions of what those constructs in the language mean, or what their structure is. This kind of makes sense? Does this look familiar? Has anyone really seen this? Who's seen this before? Wow, not many. No grammar. Who's learned a foreign language, a language that's not their native language? You didn't learn about grammar in that language? You learned about grammar, right? You learned like parts of speech, like this is a verb, this adverbs. Yeah, so these are the names of the syntactic constructs in human language. And if you've never done this before, you can represent this as a tree where you have a single root of this tree, like the sentence, and several patterns of structures that represent the different types of utterances or expressions that you can say in that language. And so one of your colleagues asked about the interpretation of words in this language. So let me give you an example of where syntax matters, or syntax is kind of real in a sense. So here's another sentence. The boy, leaving behind his friend, went to the store. So what is the subject of the verb went here?
Don't know.
Who's going here? Yeah.
Well, it's ambiguous. We don't know who that went. Is it his friend or the boy?
If I said the boy leaving behind his friend went to the store.
With a comma? With a
If I say that to you, if you didn't read it, if I just said the boy leaving behind his friend went to the store, who's going to the store? The boy, right? So if I said the boy leaving behind, his friend went to the store, doesn't quite sound right, right? Like it's not quite, something's off about that. Yeah. So commas, so you don't say commas, right? Like nobody says the boy, comma, leaving behind his friend, comma, went to the store. So you didn't have to have the commas to hear that the boy is the subject, right? Anyone disagree? Or if I said the boy walking fast went to the store. Who's going to the store? Did fast go to the store? Or did the boy go to the store? The boy, right? So, yeah, I know, like, looking at it, yeah, go ahead.
Okay, so this is like kind of not super important, but just if we're talking about language, I'm looking into it because something sounded off about it being the indirect object. I think it's the object of the preposition as opposed to the indirect object, which is a minor distinction. But
So the went doesn't have an object at all, you're saying?
I don't think so.
Okay, I'll take it. I don't know. I'm not a English grammar expert. Okay, so all right. Two things to point out here is that I think most of you, if you heard this sentence, you would understand that it's the boy going to the store, right? Not his friend. The boy leaving behind his friend went to the store. Because you can kind of, even though this is a single sequence, if we just looked at this part here, you would think, well, the friend is going to the store. But I think most, at least native English speakers, would not interpret this as his friend went to the store. Agree, disagree? Kind of agree? Or if I said the boy walking fast went to the store, no one would think fast was going to the store, right? So somehow you are understanding the fact that this here, and even some of you said, well, you corrected me, saying, well, put commas, right? So that means you understand that this is a separate clause from the boy went to the store. But there's nothing here saying, here's the subject, the boy. Here's this modifying clause, leaving his friend. Here's now the verb. Nobody said that, right? But you were still able to grasp that the boy and went were the connected parts of the sentence. Make sense? You got it, right? You still got it. Now, one theory, the kind of Chomsky linguistic theory, is that we have a built-in ability to use grammatical language. And that when hearing this, you'll actually kind of know, or when speaking this, you'll be able to kind of pause your sentence, the boy went to the store, push that onto the stack, so to speak, and start saying some other part, saying some other clause, and then come back up, pop the stack, so to speak, and continue talking about what the boy was doing. And this kind of stack-based or weight-holding state while you go on to process the language, this is exactly how computer languages, programming languages are processed in the machine. The reason this is possible to kind of, I forgot to link to this, but so Chomsky's kind of classic phrase here to show the difference between, say, the boy leaving behind, his friend went to the store. The reason that sounds off, if his friend is the subject, is because Chomsky believed that there was an internal built-in capacity for this grammar, and he illustrated this with two sentences. So he had one sentence, colorless green ideas sleep furiously. Sounds kind of right? It sounds grammatical, because we have a subject, we have a verb, we have an adverb here. But this sentence here, furiously sleep ideas green colorless. Even though both of these are really nonsense, basically, right? Like, what does this mean? He tried to design a sentence that would have no meaning. You know, how can you have a colorless green? How can you have an idea that has a color? How can you sleep furiously? So he tried to design a sentence that was grammatical but meaningless, and contrasted with a sentence that was ungrammatical, to point out that when we as humans hear this grammatical sentence, it sounds right? It sounds like a correct sentence. Or at least it has some correctness to it that sentence 2 doesn't have. Make sense? No? Yes, no? Getting some skepticism? What's your skepticism? No? No skepticism? Yeah.
Most of the issues is sleep is a verb, so isn't it? A verb can't really represent, an adjective.
You mean here?
Yeah.
Yeah, because you're already assuming that sleep must be an adjective just because of what? Because of its position in the sentence. So syntax can be thought of kind of informally as just how kind of legal orderings or groupings of words. And in fact, when we looked at our arithmetic expression, the reason that you could interpret this sequence of words as an independent multiplication was because of the syntax you had in your head about arithmetic operations. Because these are grouped in a certain way, in order, right? Like you have the operation in between the symbols for numbers, you could interpret that as multiplication. So I didn't say 1, 2, 3 plus multiplication, which there are other interpretations of. But you were able to understand that the relative orderings of these words, how they were ordered together and grouped, actually was connected to the meaning. You use that to ascribe meaning to that. So it's not enough to just know the meaning of each individual symbol. Their relative position to each other and how they're grouped, we also use that to ascribe meaning to symbols. Little less skepticism? So this Chomskyan view of linguistics is kind of the minority view these days in linguistics. But he used this as evidence that there was an inborn human capacity for grammatical language that, as I currently understand, has not been demonstrated in other animals. Language has been, but this kind of grammatical structure of languages, as far as I understand, I'm not an expert in this, has not been demonstrated in other animals. All right, questions on what syntax trees are? You guys with me on this? You guys with me? Okay. I'm not sure if you're rapt with attention or just utterly confused or just bored. Yeah.
How are they broken down? Do we just make a lot of trees for each type of word? So one tree for adjective, one for subject, one for verb.
So that So how you actually design a human language grammar? That's like a project that's been long abandoned. People use statistical approaches to analyze human language now, like natural language processing. They kind of combine, grammatical and statistical approaches, but it's largely statistical. But this grammatical view of language is preserved in the compiler world, where we use it to actually process unambiguously input languages. But you could do that for human language. It would be hard because we have a huge grammar. There are sentences of a single word, right? So you have to enumerate all of them. Yeah.
Is this good? We're basically going to be doing this for compiler instead of words. It would be like tokens.
Yeah, exactly right. So that gets into the next part. So any other questions about this just notion of syntactic structure, regardless of the philosophy behind it, that we can diagram these, I can show it here. We can diagram these sentences. We can name the syntactic structure and associate them with the orderings of words in our language. Okay. Not sure that I can't read the room. Everybody looks very stone-faced. Okay, so just to kind of highlight the connection between syntax and meaning is that you can have the same word, store. There are two sentences here. The store is closed versus squirrels store acorns for the winter. Maybe not. I guess they do it here. Do they do it in Florida too? It's the same word, right? It's the exact same symbol. And you would have no idea what its meaning is without its relative orderings, right? So what is the meaning of store here? Yeah, it's a shop that sells stuff, right? And here, does a store mean a shop that sells stuff? No, it means to squirrel away or to, place things for future use. So the meaning depends, at least in part, on the structure of the sentence. All right, so let's get back to the programming language world and look at arithmetic expressions. So let's make let's try to make a syntax tree for this, even though we don't have a grammar yet. You probably have a grammar in your head of what this looks like. So let me draw a syntax tree for this arithmetic expression. So at the root, I'm just going to call this an expression. Let me use E to make this an expression. And so let's say an expression has a left side, an operator, and a right side. Yeah?
Are we doing kind of like a stack
That's very closely related. So infix and postfix, you could think of it as a translator or a compiler between two representations. So if you, who did infix to postfix? Oh, great. Okay. So this is very much related. I don't know if you did a tree. Did you do tree, syntax trees of it? You just wrote an algorithm, right? So implicitly in your algorithm, you were actually parsing that infix notation, and you were using a stack to hold on to, just like in the example of the contentious example of the boy leaving behind his friend went to the store. You can think of a similar approach to the infix, where you used a stack in order to hold on to one of the sub-expressions in the language. This tree representation is just another way to represent that holding of sub-expression values. So, okay, well, actually, before I draw the tree, how would you let's say if you wanted to write an assembly program or do this on a calculator, how would you compute this value?
Wait, is this gonna be like for postfix, prefix kind of deal?
So this is infix. This is infix, right? So how would you compute this? Yeah.
I read it left and right unless I see an operator that has more or higher precedence than
Okay. So what operation would you do first here?
the addition.
So you would do 9 plus 3 and get 12. And then what would you do?
Continue to move from left to right, I would do subtraction of 2.
Then you'd save that result and do the subtraction. There's two operations here, right?
Yes.
So we can capture that in a tree with, let me do it this way. So here we did the 12 first. We did the left side first. So if we just had 9 plus 3, we could capture the syntactic structure of this as an expression that contains a left side, a right side, and an operator. Yeah.
What's the E? Is that expression?
Yeah, let's say E means expression, just so I don't have to write expression in my terrible handwriting every time. So let's say E designates an expression, just like we said subject. So nowhere in this expression does anyone say this is an expression. But we can name the syntactic structure and record it explicitly in this tree, just like we did with sentence diagramming. So we can say, all right, an expression consists of a left side, a right side, and an operator. So we can start defining the structure of this expression explicitly by naming what the structure is and defining a kind of schema for what it looks like. So we can say, all right, an expression consists of some left side. So let's say it can consist of a number on the left side, an operator, let's say it's always plus, and a number on the right side. So we can make a kind of template to represent what all syntactic structures look like for these expressions. Kind of make sense? It's a little template that says, well, okay, an expression is a number, operator, number. So here I mean n means number. Now, if we want to have multiple operations in a single expression, we can expand out the meaning of expression. So here in this expression, we actually have two operations. But implicitly, there's a saved value here that we never really say. We don't tell anyone, okay, here's an expression, first do this one and save its value. Nobody ever tells you that, right? You do that in your head. And so we can make these structure of this explicit by defining this kind of template that describes what all of these syntactic structures look like. So to capture that intermediate result, we can also allow expressions to have another expression as one of its operands. And so here I can say, well, all right, we have a template for E, can have E on the left-hand side, a minus operator, and a number. Does that kind of make sense? So this E here has an E on its left-hand side, has a number on its right-hand side, and it has an operator as a second symbol in its structure. Questions on that? Does that kind of make sense?
Yes.
Yeah.
So we're just defining rules.
Exactly, yeah. You're defining rules that capture all the possible syntax You're defining syntax rules for this language. So you can kind of philosophically assume that in your head, you're kind of processing all of this grammar implicitly. At least that's what a machine is going to do. Processing this grammar implicitly and then using that syntactic structure in order to interpret the meaning of these symbols. Remember, the symbols don't have meaning on their own. Yeah.
So like, I would assume you can kind of do this like with regular expressions, where you like define what is it, the alphabet or something?
Right. So yeah. So actually, okay, good. Who learned about regular expressions? I think this is in discrete. I don't know if it's required for this class. So not everyone learned about it. So regular expressions are a formal way to describe languages. So languages are just sequences of strings, and an expression defines constraints on what legal strings are in that language. Now, if you take big discrete, you'll learn that regular expressions cannot express syntactic structure. They're not powerful enough to do that because they're finite. They have a finite amount of state. These grammars require an unbounded amount of state. Yeah.
I was going to say that we have kind of learned regular expressions how to do
In where?
object-oriented programming.
Oh, the principles of object orientation. They teach it. Okay. So that's also not required for this class. So I can't assume. Yeah. I think I won't have time to do it here. Take discrete 2. But it basically comes down to matching parentheses. So you can never write a regular expression that will match an arbitrary number of parentheses because you always have to grow the number of discrete states that you need to represent it. It's called the pumping lemma is a proof or a disproof of it. So take big discrete and you'll learn all about that. Okay, so let me clean up this grammar a little bit. So let's make a much simpler version of this grammar. Let's just say any expression is an E followed by an operator followed by another expression. And let's say an E can also just be a number. And let's define my operators to be plus. I'm going to use a little regular expression syntax here. Plus, or, minus, or multiplication, or division. Everybody with me on this? Any questions on this? I'm just using this pipe to mean or. And let's say a number is single digits, 1, 2, 3, 4, all the way up to 9. So this is a kind of template that describes that describes the syntax of all possible expressions in my arithmetic expression language. And so using this, I can take any expression in my language, like 1 plus 2 times 3, and I can figure out how these expressions are grouped together and whether they actually are an expression. So if I had another symbol here, like a caret, because this caret is not in my grammar, or if I have an expression like 1, 2, 5, this is also not in my grammar because I only have single digits in my grammar. Or if I had 1, 2, 5 plus, if I had, for instance, 5 plus times 3, this can't be represented in my grammar, right? There's no way to represent this in my grammar. So this defines not only what the legal expressions are, but also removes all non-expression sentences. Okay, so let's show how we can derive a tree for this expression. So the way this works is you start at the first symbol in your language, and you can think of this as a schema that defines what the children nodes are of your tree. So E will always have, in this case, we kind of have to guess which one to use. But let's say we guess right and say, well, all right, it's going to be E followed by an op followed by E. Question so far? With me so far? Can use this as a little template to tell us what the children of our tree are. And then here, E can either be another one of these E op E expressions or a number. Which one should we pick? Let's say another E. Okay. So E followed by op followed by another E. What about this E here? Or actually, let's continue that tree. What about this E? Should we use this first rule here or the second rule? Yeah. Second rule. So why? Why the second rule? Yeah, if we did the second rule, there wouldn't be enough numbers just to fill in all of the parts of the tree. So there are algorithms for actually doing this. We're going to do this very informally. Okay, so num, and that num, we can just pick the first number in our sentence. Op is obviously going to go to the plus here. Now what about this e? Num, who says num? What about e op e? So if we did e op e, we'd end up with 3 e's, and there's only 2 numbers left, so it wouldn't work out. So I'll leave this as an exercise for you to figure out why it wouldn't work out, but if we have this as a num, that num maps to 2, and that leaves star as the op, and this e as another num for 3. So deriving this is a tricky algorithm to do itself, but seeing this tree, does this tree make sense for our rules? We sort of get the connection between the trees and the rule. Yeah?
What if it's ignoring the order of operations?
Aha, okay, so what does order of operations have to do with this here? So why is the plus first here? Yeah.
Well, say we're doing well, it actually depends on the coding language. If we have Fortran, this would be correct, but if we did not have Fortran, so if we had C or Java, this would not be correct.
Okay, so this grammar is correctly parsing this. We can make a tree for this sentence here. So this grammar doesn't have anything about order of operations encoded in it. Now, you're objecting because you want order of operations, but in order to understand why we have order of operations, let's see how we can actually interpret this tree, actually ascribe meaning to it. So the syntax part gives us the grouping, the orderings of words, how they relate to the grammar constructs in our language. But in order to finish ascribing meaning to this, we need to interpret it somehow or compile it. So let's do the interpreter approach of this. So let me give you a very simple interpreter algorithm for this. We walk the tree in a post-order fashion, and if there's a leaf node, we just translate its symbol value to its math value. So I'm going to denote that like this. Now, this looks very tautological, but just think this is the ASCII code and this is the machine code. So this is the ASCII representation, and this is the machine code representation. So I'm going to translate the ASCII representation to the machine code representation when I see a leaf node, when I see this num node. And when I see an expression, what I'm going to do is I'm going to take the expression on the left, I'm going to take its value, and I'm going to take the expression on the right, its value, and I'm going to compute a function that corresponds to the operator to get its value. Yeah.
It's going to be recursive algorithm?
Well, it's going to end up being recursive, right? Because when I'm here, I need to get the value of the left side and get the value of the right side. In order to get the value of the left side, I need to pause and evaluate the value of E. So to evaluate the value of E, I need to get the left side. I have a rule here that tells me how to evaluate that left side if it's a num. And that tells me that its value is, let me use a different color here, its value is machine code 1, because I just convert the ASCII code to machine code. And its right value is machine code 2. I just convert the ASCII symbol of 2 to machine code 2. And then in order to evaluate E, I take whatever the operator is, which is plus, and I use that as a function to compute 1 plus 2. Does this syntax look uncomfortable to you? All right, let me do this in a different way to make this less ugly. So if I have an op, let's say that I take plus and I convert it to the add function, and minus and I convert it to subtract function. That seem a little better? So I'll make red to be my machine and black to be the ASCII. So here, op is converted into the add instruction. And then the rule for E is to take whatever the op is, take whatever the value of the left is, take whatever the right is, and apply the function to those two values.
Sorry.
Questions on this? Questions on this? Is this confusing? Yeah.
Isn't the homework like?
You mean the calculator project?
No, the homework for today.
The homework will be making a grammar. We'll be writing a grammar. So to review, we start at the top, we do a post-order traversal. When we reach a leaf, we look at the rule for how to interpret enum. So the rule is to turn that ASCII value into machine code. We do that for both leaves. Turn that ASCII value into machine code. When we see an op, we convert that into a function that corresponds to the operation that we want to do. This could be, for instance, assembly code if you're translating this. And then the rule for seeing this eop, actually, we could write the rules here. That would probably make it clear. But the rule for E, when it's E op E, is to construct this function call from whatever the op is and the two values on the left and right side. Questions on that? Seems like it's clear to some, maybe not clear to others. All right, so continuing this, how do we get the value of this E?
Work your way up.
We take whatever the value of the left-hand side is, whatever the value of the right-hand side is. So the value of the right-hand side is what, based on our rules? It's 3, because this rule tells us to convert an ASCII number into its machine code representation. And how do we compute the value of this E? We take the op, converted that ASCII symbol into some function that's actually going to compute the value. And we could represent this in a number of ways. We could either leave this add in place, or we could compute it on the fly here. Let's say we just leave it into place. Then this is what the resulting value of this tree is going to be. Yeah?
How would optimizations work? That's how the tree is.
How would okay. So optimizations would look at this representation and try to change. So for instance, if we can add 1 plus 2 at compile time, we can just compute it and then convert this into mult 3 times 3. So that would be an optimization, right? You take this function, that's this call that's produced by your tree, and then convert it into another call that has fewer operations. That would be an optimization. Okay, questions on this basic idea of traversing the tree and converting or interpreting each symbol of the leaves and interpreting the meaning of these constructs in terms of some computation. Any questions on that process of traversing the tree and computing the value of this expression by traversing the tree? So if you did the infix to postfix, you did something very similar. You actually traversed that tree, although you did it in a very shorthand way by using a stack. But you effectively traversed this tree, and your output was not the value, but your output was a translation of that tree. And so maybe next time I can start with that to kind of give you a basis. So who's done the infix to postfix before? How many people have done it? Who's not done it? Okay, so it seems like everybody has. This is basically the same thing. So next time, let me make a note to frame that next time, since you all have that as a basis, to frame that as this kind of translation. Okay, so all right. So for homework, you've got this exercise to write this grammar. Do your best. I know I didn't go over in detail the grammars, but do your best to write a grammar similar to what we have now for reverse Polish notation. Feel free to start the calc project. You don't need to understand parsing to do it. You can just copy the work. And then next time, let's finish up parsing, and then I'll show the intermediate representation. We'll get started on our compiler project. All right, thanks, everybody.